Somewhere in the darkness, 146 light years away, there may be a world that looks uncomfortably familiar. Not in the way science fiction promises. No glowing cities or alien oceans, just cold rock and dim starlight, and the unsettling possibility that Earth may not be as rare as we once thought. Because recently, buried inside old data from a retired space telescope, scientists may have found something we've been searching for our entire history. Another Earth-sized planet orbiting a sun-like star in roughly the right place. Subscribe to Territory, because this is your space. For most of human history, planets around other stars were pure speculation. Until the 1990s, we didn't have proof that any star besides the Sun had planets at all. Today, we've confirmed thousands by watching how starlight behaves. When a planet passes in front of its star, it blocks a tiny fraction of light. The star dims, just slightly. If that dimming repeats at regular intervals, you may be watching a planet cross its star like a shadow. This is how NASA's Kepler Space Telescope changed astronomy forever. Kepler stared at one patch of sky for years, monitoring the brightness of over 150,000 stars, hunting for patterns too small for the human eye to notice. Most of the planets it found were nothing like Earth. Hot Jupiters, lava worlds, planets so close to their stars that a year lasts a few days. But occasionally, Kepler found something quieter. A small planet on a long orbit, circling its star at just the right distance. That distance matters more than almost anything else. It's what astronomers call the habitable zone. Despite the name, it doesn't mean a planet is habitable. It doesn't mean life exists there. It doesn't even mean the planet has water. It simply means one thing. If the planet has the right atmosphere, liquid water could exist on its surface. Too close to the star, and water boils away. Too far, and it freezes solid. Earth sits in a narrow comfort zone, a coincidence so precise that for centuries it was used as evidence that we must be unique. So when astronomers find a planet orbiting in that same narrow band, it gets attention. Then they look for signs of water, because water changes everything. Which is why the search for life beyond Earth is, at its core, a search for environments where water might persist. Now fast forward to the present, Kepler is gone. Its mission ended years ago. But space missions have a strange habit. They often outlive their original purpose. Recently, scientists revisiting Kepler's old observations noticed something unusual around a star known as HD 137010. A single dip in brightness, one that looked planetary. The signal suggested a world only slightly larger than Earth, about 6% bigger, orbiting its star once every 355 days, almost the length of an Earth year. Not only that, the planet orbits roughly the same distance from its star as Earth does from the Sun. So what's the catch? Dubbed HD 137010b, the planet's star is cooler and dimmer than our Sun, which means even at an Earth-like distance, the planet receives less energy. Initial estimates suggest surface temperatures could hover around -70 degrees Celsius. That's colder than Antarctica, colder than Mars at times. And there's another problem. So far, astronomers have only observed one transit, one shadow. That means the planet's existence isn't fully confirmed yet. It could be real, or it could be a false signal. But if it is real, it represents something quietly profound. Because Earth itself has spent large portions of its history cold. Frozen oceans, global ice ages, snowball Earth events where glaciers reached the equator. And yet, life persisted, life adapted. Life endured. A planet at -70 degrees Celsius is not necessarily lifeless, especially if it has an atmosphere, or internal heat, or subsurface water. And habitability is a spectrum, so the exoplanet, cold and distant as it may be, sits somewhere on that spectrum. Now, why is this discovery important? Every Earth-sized planet found in a habitable zone narrows the gap between life is impossible elsewhere and life is inevitable. If rocky worlds form easily, if habitable zones are common, if water can persist under a wide range of conditions, then the question changes. Not whether life exists elsewhere, but how often. In the coming years, telescopes like the James Webb Space Telescope may be able to study planets like this in more detail. And who knows what this exoplanet has in store for us? What do you guys think? Comment below to let us know. And while we're talking about potentially habitable worlds, let's turn to a planet that drew significant attention last year when the James Webb Space Telescope observed it. This is K2-18b, an exoplanet 8 times as massive as Earth, orbiting a red dwarf star about 120 light-years from Earth. Discovered in 2015 by the Kepler Space Telescope, the planet has since stood out as a subject of keen interest among astrobiologists because it lies in the habitable zone of its star. As such, it was quite obvious that once the James Webb Space Telescope was launched, one of its objectives would be to turn its gaze toward the planet to look for signs of life. And in 2023, K2-18b made headlines when researchers reported that JWST observations of the planet were consistent with a habitable ocean world. To make matters more interesting, the same research team reported weak evidence for dimethyl sulfide, a compound that on Earth forms almost exclusively due to life. This led many onlookers to the eyebrow-raising conclusion that K2-18b is not just habitable, but inhabited. But there was only one way to know for sure: more observations. It's been 2 years since then, and repeated analyses of the exoplanet's atmosphere by the James Webb Space Telescope now suggest the presence of several molecules that, on Earth, have only one known source: living organisms. Last year, Dr. Madhusudhan and his colleagues got a second chance to look for dimethyl sulfide, and here's how they detected the molecules in the atmosphere of K2-18b.
So the technique we used to determine the atmospheric composition of the planet is known as transit spectroscopy. What is happening is that you look at the planet as it transits in front of the host star. So the atmosphere of the planet, some of the starlight goes through the atmosphere of the planet before reaching the telescope. And the atmosphere, the molecules in the atmosphere absorb some of that starlight. So by looking at a differential measurement when the planet is in front of the star or when it isn't, you can extract how much absorption is happening in the planet's atmosphere. So 2 years ago in 2023, we reported a very tentative inference of DMS on this planet with a different set of observations with a different instrument in the 1 to 5 micron range. But the evidence was very tentative, so we looked this time at the planet again in a different wavelength range. And what we are finding is significantly stronger evidence at a 3 sigma level for the presence of either DMS or DMDS or both. Now, DMDS, like DMS, is also a strong and unique biomarker here on Earth and had also been predicted to be a biomarker on planets with hydrogen-rich atmospheres. And that is what is new, is that there is a possibility of one or both of these molecules to be present in the atmosphere at a credible level of significance.
What's surprising is that this time, the signal for dimethyl sulfide came back even stronger than last time. Add to that, they also found dimethyl disulfide. And no matter how many times the scientists reanalyzed the data, the signal stayed firm. Their conclusion? K2-18b might contain an astonishing abundance of dimethyl sulfide in its atmosphere, potentially thousands of times more than what we find on Earth. If true, it could mean that the planet's high oceans are teeming with life. So, let's come back to the big question. Does this confirm life beyond Earth?
This is one of the most profound moments for me personally, as well as an astronomer, because for the first time in the history of our species, we may actually be seeing signs of life elsewhere. On the other hand, this could also be a signal of a new chemical process that is not produced by life. And even that is a monumental breakthrough, because however you put it, we are seeing new chemical processes on a planet that could be habitable. And we have shown this in theoretical studies that that was possible. So this is, in my view, a transformational moment, not just for planetary science, not just for astronomy, but for finding our place in the universe as a species.
While this marks a significant step toward discovering life on an alien world, not all scientists share Dr. Madhusudan's enthusiasm. They argue that even if K2-18b has a hydrogen atmosphere and a surface ocean of water, these factors alone wouldn't confirm the presence of life, but merely suggest that the planet could be potentially habitable. And while the telescope did detect CO2 and methane on the planet, these gases are regularly produced by non-living processes. For example, NASA's Curiosity rover has detected methane on Mars seeping from the surface of Gale Crater. But scientists haven't found convincing signs of current or ancient life on the red planet. Some scientists believe that there could be non-living ways to produce these compounds on other planets. For example, a recent preliminary paper reported evidence of dimethyl sulfide after analyzing data from Comet 67P. You see, the best biosignatures on an exoplanet may differ significantly from those we find most abundant on Earth. So, how do we interpret the telescope's data? A team from NASA's Research Center and the University of Washington approached this question by using two sets of models with the available Webb data. The first model describes rocky planets with surface oceans, with and without life. The other describes gaseous planets without a surface and without life. Both models predict the planet's photochemistry, the chemical reactions in the atmosphere driven by photons from the host star and its climate. The team found that K2-18b is unlikely to be a lifeless water world because such a planet wouldn't have enough methane in its atmosphere to match JWST observations. So, it looks like a water world with microbial life is more promising, with simple methane-producing organisms that may be able to generate the supply of methane seen in the planet's atmosphere. But despite the excitement, the team found that the uninhabitable, gas-rich exoplanet model also fits the data well and may present fewer challenges. The ocean world model not only requires life to explain its atmosphere, but also struggles to reconcile the needed cool surface temperature with the likelihood of a runaway greenhouse effect. What this means is that the planet might be too hot for life to be present at all. And hence, the team suggests that efforts to look for life on exoplanets should first test planetary temperatures to ensure that they are not too hot to host oceans. But this isn't the last word on K2-18b. There are features in the planet's spectrum that aren't well fit by either a lively ocean world or a lifeless, gas-rich planet, and both models have their challenges. These results are the product of just two observations, with many more on the way. This means that our work here is but an early demonstration of what Webb can observe in habitable zone exoplanets. Future data from JWST might dredge up a detection of ammonia, which would point to a gaseous planet, or dimethyl sulfide, which would tilt the scales considerably toward an inhabited water world. In the meantime, the hunt for habitable planets goes on.